Good morning. Thank you for coming. I see a few more people coming in. All right. So today I'll be talking about MLS, messaging layer security. And to give you a bit of context immediately, MLS is a new protocol for end-to-end encrypted messaging. And it is also an IETF working group. And the question is, why is this important now? And this is what I'm going to focus on during the talk. To introduce myself quickly, my name is Raphael Robert. I work for Wire, which is a secure messenger and collaboration platform. It's open source, it uses end-to-end encryption. And I've been working there pretty much since day one, when it was founded back in 2012. And Wire is one of the companies that is part of this IETF working group for MLS. It co-initiated the idea back in 2016, but it's not the only company that takes part there. So we have a number of other companies you might recognize here, and most importantly, we also have a number of universities who take part in that working group, which is very important for new protocols. So first we're going to briefly look at the current status of where we are today with secure messaging. So we have a lot of secure messaging apps today, and some of you probably use some of them. Some of them use very similar protocols, but others are also different. But all of them more or less try to solve the same problem at the end of the day. And what is problematic is that because the protocols are different and the details are different, the levels of analysis are also really different across different messengers. And most of them maintain their own libraries. And so we have a bit of a zoo of different security levels, of different security properties. And if we take a step back, and look a bit at the history of security properties in secure messaging. So it really became popular in the 90s with PGP. Today we have OpenPGP as well as MIME for end-to-end encryption for emails. And the two properties that were introduced back then were confidentiality and authenticity. Confidentiality is simple. It simply means things are encrypted. Third parties cannot look into it. Authenticity means you know who sent it, you know who encrypted it, or you know who signed it. So this is the base layer of end-to-end encryption these days. Later on, there was the off-the-record protocol, I think around 2005, that added two new properties, forward secrecy and deniability. Forward secrecy means that messages that were encrypted in the past can no longer be decrypted in the future. If there is a compromise, an attacker gets some key material, that key material is not good enough to decrypt all of the messages from the past. Deniability is a very controversial property. Whenever I speak about it, there are about 50% of the people who say that it's a very important one to have. It's absolutely necessary. Others say that it's absolutely unnecessary. It's very divisive. And what it means essentially, on different levels, the idea is that messages, for example, can be authenticated in a way that the recipient understands that they're authenticated, but the recipient cannot prove it to a third party. That message was authored by a certain person. And then there are more fine-grained levels of deniability. For example, It could be deniable that a conversation ever happened as a whole. And so this was really coined by the off-the-record protocol, and they split up deniability in even more levels. And then we have the double ratchet algorithm, which is the basis for the Signal protocol these days. And that is essentially an adaptation of what the off-the-record protocol did in terms of security guarantees. And it also introduced a new one, which was called future secrecy. And these days, that is mostly referred to as post-compromise security in academic circles. The term is a little more telling what this is about. So you can think of it as the exact opposite of forward secrecy, where we care about messages from the past. With future secrecy or post-compromise security, it's about the future, as the name says. And the question there is, once a compromise has happened of an endpoint, is there a way to recover from that on the same device? And if yes, then you do have post-compromise security. So what about groups? Because all of the protocols I've talked about so far, they're for one-to-one communication. Email, of course, I mean, you can send an email to more than one person, but you will have to encrypt it individually. And the same is true for the off-the-record protocol and also for the Signal protocol. But the reality is we use messaging in groups a lot. Even in a one-to-one context, if you have more than one device, to some extent that is already a group of devices now. And the practical problem here is that pairwise protocols, as we call these one-to-one protocols, they cannot just be extended so that they can be used in groups. You cannot just add more endpoints to the two you already have. So you have to resort to something else to address that particular problem. And so what typically happens, for example, in the case of Signal, also in the case of Wire and other messengers, the pairwise channels, they're being superposed to simulate a group. So what that means is that if you send a message in a group, you individually encrypt it to every recipient in the group, or even worse, you individually encrypt it to every device of every recipient in the group. So that is not very efficient. And so it might be that at the end of the day, because of these efficiency problems, you might go for a trade-off between security properties and scalability. And we're going to look into that in more detail later. So when you create a group on top of pairwise protocols, you do that at a level that is really above the initial protocol level. And so every messenger does this differently. Even if a messenger uses the same layer underneath, for example, there is a number of messengers now using the Signal protocol like WhatsApp and Facebook Messenger and others. What they do with groups on top of that is extremely proprietary. So you have this layer of the secure one-to-one protocol, and then you have this group management layer on top of that. And the one-to-one protocol is often quite well analyzed. Again, in the case of Signal, that is true also for other protocols. There's been some scrutiny also in academia, but the group management layer is typically not scrutinized at all. So if we go back to this idea of having a trade-off between security properties and good scalability, if we try to have a very simple chart here, PGP would be in the lower left corner because it doesn't really have modern security. It doesn't have forward security or, forward secrecy or post-compromise security, and it doesn't scale well. Then there are these messengers that are based on protocols that are more modern in a one-to-one setting, and we call this client fan-out because it's the client fanning out the same message to all of the recipients. So they have modern security guarantees, but they still don't scale very well. And then we have a concept called sender keys, which in a way it's an adaptation of the Signal protocol. It's a hack used by WhatsApp, for example, by Facebook Messenger, also by Matrix. And the idea there is that they try to improve the efficiency a bit by sending out an encryption key to everybody in the group and using that key to encrypt future messages so that they don't have to individually encrypt them. They can only do it once. But sending out the key is still very expensive. So you gain a bit of efficiency once you only send out messages, but the setup is still expensive. So this is somewhere in the middle. It scales a little better than the rest, but the security is not that great anymore because you tend to not rotate keys or only rotate keys when it's absolutely necessary because it is still expensive. So the obvious question is, could we have anything in the upper right corner here, something that has very modern security but that also scales well in larger groups? So what would be the objective? So if we say, okay, let's do a new messaging protocol, what would we like to be in that protocol? If we were to write up a wish list, what should be on that wish list? So if we start with the security properties, of course we want confidentiality and authenticity, that's the strict minimum. Obviously we want forward secrecy. We want post-compromise security. It sounds easy, but this is really what makes things actually quite difficult to have that. We want deniability. As I said, it's a very divisive thing, so maybe we want it just optionally, not for everybody. And then we also want groups. And we could come up with some new security properties. So for example, in a group it would be nice to have authentication of members in a group. Because right now, if you recall this group management layer, the way most messengers work is that there is no particular guarantee that all the clients in a group see the same set of members. And so you either trust what other members in the group told you, or you trust the server, for example, but you don't have any cryptographic guarantee of who's really in the group. And when you receive a message, for example, you cannot tell for sure who this message was encrypted for, except for yourself. So there's some room for improvement here, clearly. So what else do we want that is maybe not security related, strictly speaking, when we do a protocol? So we want it to be asynchronous. And this is what made all the difference between the off-the-record protocol and what we now know as the Signal protocol. The off-the-record protocol was designed to be in an online session. If you remember the old days of Skype, for example, both sides had to be online at the same time for messages to arrive. And so this is not something that works anymore in the world of smartphones, because smartphones are sometimes online, sometimes offline. Sometimes you think you're online, but you're not really online. So things have to be asynchronous here. You cannot wait for people to come online. Another prominent example is in Telegram, for example, when you go for these secret conversations where there is actually some sort of end-to-end encryption taking place, you have to wait for the other party to come online first before you can initiate such a chat. So that's not a great user experience. Of course, we want groups, so we want support for large and dynamic groups. Dynamic meaning people can come and go frequently, and we want that to scale efficiently. We also want multi-device support, because the reality is most of us have more than one device we use for messaging. We would also like to not be tied necessarily to only one service provider for messaging. It would be nice if the protocol would inherently support more than one server or more than one service. And this is generally known as federation. And last but not least, we want this to be usable. So we don't want an academic effort that looks really good on paper, but that cannot be implemented because somebody made some assumption that doesn't really hold in the real world. So this part is really important, so that a new protocol can actually be a replacement for either nothing or whatever was used previously in messengers. What else could we wish for, since we have the liberty of coming up with wishes here? It should be an open standard. The specification should be there for everybody to read, for everybody to implement, and for everybody to criticize as well, and to analyze. That's very important. And the other thing is that if you don't want to implement something yourself, there should be enough libraries you can use. And we've a great example there is TLS, for example. So TLS is an open standard, anybody can implement it, but typically what most developers will do at the end of the day, they're going to pick a library that they like and are going to use that. So this is also important. And I already mentioned the security analysis. This is something relatively new in the design of protocols. So far, it used to be the case that after a protocol was created, the security was analyzed afterwards. Then it became a little more frequent that during the design phase of a protocol, academic consideration was already accounted for. And a great example there is TLS 1.3, where developers have worked hand in hand with academia to come up with that protocol and to have a security analysis during the design phase already. So now let's talk a bit more about MLS and see if MLS could potentially be the answer to this wish list and these questions. A very brief overview of the history. In 2015, an academic paper was published by the University of Oxford and Facebook, and they thought about solving the problem of having more efficient messaging in very large groups, and came up with the idea of using binary trees for that. So ART stands for asynchronous ratcheting trees. So that was the first foray on the scientific level. In 2016, a number of companies gathered, actually at the Wire office, incidentally, and they all agreed that there is a problem with messaging. We need an open standard, and we need it to be more efficient. And so a little less than 2 years later, in March 2018 at the IETF in London, there was the Birds of a Feather meeting, which is the inception of an IETF working group, and it became officially a working group in May 2018. And ever since, they've been regular meetings. So there are some analogies between MLS and TLS. It's not only the name. The idea is to take all the good ideas from the design process of TLS and to also apply that to MLS. So conceptually, if we look at the scope of TLS, we have a certain transport layer over which previously we would send message content like HTTP, SMTP, SIP, etc. And TLS fits right in there and add security where previously there was no security. And it has one interface, essentially, and that is for authentication. So you all know that from TLS, there are certificates, you can verify them. There's certificate authorities. So there is, in a more abstract term, there is a PKI, and that is the interface to TLS. And so we want MLS to be similar in a way that we have a base layer where we now take TLS, or at least something similar, where we have some transport encryption between clients and servers, but it's not end-to-end yet. And then we have some application layer on top of that for typically messages, but it could be files, could be other things. And so we want MLS to fit right in there, just like TLS does. We have the security protocol, and we have a similar interface for an authentication service, which again, like TLS is a little outside. So certificates are not part of TLS. They live next to TLS conceptually. And we want to have the same distinction here, so that on the server side of MLS, we only have two components. There is one authentication service, which is not particularly specified how it works. The whole idea is that it can provide some authenticity for users. So users could have signing keys, certificates, that's really up to the application. And then there is a delivery service, and the delivery service is really just a coordinator of messages. So users can have multiple clients, and we have some sort of a bus where messages are sent from a client to a server, and the server sends them out. And that's pretty much all that is happening on the server side. But there are also a lot of differences between MLS and TLS. So for example, TLS is conceptually a client-server protocol. So we have two endpoints. In MLS, we have a lot of endpoints. It's designed for groups. And we also have very long-lived sessions. TLS sessions are typically very short, a few seconds. But here we could have sessions in a group that can last for months or years even. We also have a lot of mobile devices involved. And we have to design for that. And the scope here is really for human-to-human communication, whereas TLS is actually a machine-to-machine communication where there is no human interaction needed as such, unless you have self-signed certificates. Probably all have had that situation. And so what's really different here is that the probability that a member gets compromised during one of these really long-lived sessions of MLS is a lot higher than with TLS. So this is something that we need to account for. So going back to forward secrecy and post-compromise security, to put that in maybe more understandable terms, if we assume that at some point an endpoint will get compromised, we have forward security that will protect whatever happened before the compromise. And then we have post-compromise security that tries to cover whatever happens afterwards. And so this is newer conceptually, because the idea here is that an endpoint gets compromised once. It's not a permanent compromise. So for example, somebody has access to a computer once, or finds a hard drive, gets a copy of that, gets a copy of all of the cryptographic material that is on the endpoint. But we want the endpoint to be able to recover from such a compromise, and we want to keep this window around the compromise as small as possible, so that an attacker, if they ever get their hands on key material, that the damage they can do is as limited as possible. And the very obvious answer here is to rotate keys as frequently as possible. So if we try to decompose the evolution of a group chat in two sections, for example. So imagine Alice creates a group with Bob, and then they start in a group of two, and we call this an epoch. So we don't know how long that will last, but we try to divide time into epochs that are separated by certain events. So an event could be Alice adds Charlie to the group now. And so this initiates a new epoch. Or Bob updates a key for the inside the group, or Alice removes Charlie. So for every epoch, we want fresh key material, at the very least. So that means that between epoch 3 and 4, for example, when Alice removes Charlie, in epoch 4, the key material that we use will not be known to Charlie anymore, because Charlie has been removed. And likewise, between epoch 1 and epoch 2, when Alice adds Charlie, Charlie should not have access to the key material used in epoch 1, because that was specific to the conversation between Alice and Bob. But we can even be more fine-grained than that, and if we zoom in to epoch 1, for example, we would also like every message to have its own key, essentially, within the epoch. And the idea here is that both Alice and Bob, who were the only members at that time, have the same key material in that they could derive the same keys independently on their side, and then they can use this key 1, 2, 3, etc. to encrypt the messages they're going to exchange in epoch 1. So before we start, before we can initialize secure communication, we always need some initial key material. We know that from PGP, Signal has a concept of pre-keys. So in MLS, we call them init keys, and they're keys that are published ahead of time by clients that can be retrieved through the delivery service and are generally available to initiate a secure session. So they contain credentials and a public key, more or less, and some more metadata that is relevant. This part is not particularly new. What is really new is the core protocol of MLS. It started with ART, asynchronous ratcheting trees, and then we moved on to a concept designed at INRIA in Paris called DefCamp, which is similar in the sense that we also have binary trees here, which we use for efficiency, and we'll see why in just a minute. But it is a lot more flexible than ART. So ART was not really designed for dynamic groups. There was no clear mechanism of how you can add and remove people, which in the real world is of course a problem, because you don't just create one static group forever. You want to add and remove people. So we start by having a binary tree and putting all the members from A to F at the bottom, which we call the leaves of a tree. So if you've never seen a binary tree before, they're trees but upside down, so the leaves are at the bottom and the root is at the top. And essentially we just take these init keys we have and put them there, and then we can see what we do with that. And we have these intermediate nodes above that, and at the very top we have the root. And there is one invariant that we define, and the invariant is that every member at the leaves knows the secrets that are stored in the nodes above them. So in this instance, A, for example, will know the secret that is stored in G, in J, and finally in K. Again, this is just a definition at this point. And we define that K, the root, is essentially a group secret known to everybody, because everybody should know that as per this secrecy invariant. So if we follow up with that, we get a very nice property here, and that is that we have subgroups in the tree. So we have intermediate nodes that have children, and since all the children know the secret of the intermediary node, what we can do is we can encrypt secrets to an intermediary node. So for example, if we want to send a secret to C and D, we don't have to do that individually anymore. We can send the secret to H, and then C and D can decrypt that through a CAM mechanism, for example. So we've already become more efficient here. And then likewise with J. If we send a secret to J, we have effectively sent a secret to A, B, C, and D. And of course, if we send it to K, we send it to everybody. So we have subgroups, which is extremely practical to be more efficient. And of course, the private key of the root, K, here is known to everybody at any given time. So now we need some abstract operations to work on groups, and they're very intuitive. So one is you create a group, you add a member, you remove a member, and then there's one that is a little less intuitive. It's called an update. And the idea here is that we update the key material in the tree, in particular in K, so that we can get some freshness, have some fresh key material for the group. So let's look at this mechanism first for update. So imagine F wants to update the group key in order to reduce this window around the compromise, or the potential compromise. So what F does, it generates a fresh leaf key in red here, And then it takes the secret of that and it will literally hash it and store the hash in I and hash it again and store that in K. And so the path from F to K, we call that the direct path because it's direct from F to the root. So what happened now is that we have a new group secret in K that is whatever was in F hashed a number of times depending on how tall the tree is. So F is fine with that, but nobody else knows about it. So what we need to do now is to tell the rest of the group what the new group secret is. We could, of course, tell everybody individually, but that would not be efficient. So what we do instead is we reuse these subgroups. So next to the direct path in orange here, there's another path in blue, which is the siblings of the orange path. So sibling is when you have nodes in a tree that have two children, then these two children are siblings to each other. So J is a sibling of I, and E is a sibling of F. So all we need to do now is to encrypt these new secrets to E and J, and that means that we have effectively encrypted it to everybody in the group. So the blue path is called the co-path. So it's a little complicated when you see it for the first time, but after a while it starts to make a lot of sense. And so when we create a group, we create it with a completely empty tree where we only populate the leaves. And so the problem we have here is that this is not very efficient because we don't have these subgroups to encrypt to. So initially we have to do operations, again, individually to all n members of the group. But we can very quickly make it more efficient by actually having each leaf or each member do an update. And as they do so, they will populate their direct path all the way to the top. And if just a few of them do that, then the top of the tree gets populated very quickly. And you can again use these subgroups to reach a lot of members. So when we want to add a member to the group, we add their init keys at the leaves. And then they, in turn, when they come online, they will update. So what if we want to remove somebody from a tree? Say we want to remove D now. And A wants to do that. So A sends a message to the rest of the group, or to actually everybody, including D, saying, we want to remove D, or I want to remove D. And so what we do now is that we have to erase some nodes here, because there is a secrecy invariant that says that everybody should know the secret on their direct path. Now, since we remove D, D is not allowed to know anything anymore, so we need to delete everything that is above D. And once that's the case, we have effectively evicted D, but we've also destroyed the tree a little bit and made it less efficient. So what happens here is that we don't have a whole group anymore, we have a bunch of subgroups. So we have subgroup G with A and B in it, we have C, which is its own group, and we have I, which has E and F in it. And in order to restore the efficiency here, we need an update again. So ideally C would do a key rotation if C was online, and that would restore everything except for the leaf node of D, and the whole thing would be efficient again. But it doesn't matter, it could also be anybody else in the group. In this case it would be A, because A was the one who initiated the deletion. And so when A does an update, then all the nodes above A will have values again. So we have two types of messages in MLS. One is the control messages, and these are the messages that actually control these base operations like create, add, update, and remove. And so the protocol mandates that these messages have to be in a certain order, because it does make a difference whether you add someone first or remove somebody else first. And also cryptographically, this is necessary because not all operations can be commuted. And then we have what you actually suspect in a messaging protocol. We have application messages that are typically text messages, but could be anything else. And those don't have to have this strict order. We can be a little more relaxed there because they're per sender. So first of all, the order only needs to be there per sender. It doesn't matter if two people speak at the same time in a group. Their messages are not going to interfere. Whereas on the per sender side, we just need to make sure that they're not completely out of order, but we can tolerate a little bit of confusion there. And so how do we ensure that the global order is guaranteed for the handshake messages? So this conceptually happens on the delivery service, meaning on the server side. So this is the one job the delivery service really has to do, and that is to make sure that there's no race condition between two members of a group trying to issue a handshake message. So we need that conflict to be resolved, and there has to be a winner and a loser. And if we go back to the efficiency problem a little bit, so this conceptually is what a full mesh looks like if we superpose these one-to-one connections. So this is the worst case that we don't ever want. So in pairwise sending, I already mentioned it briefly before. If we send out a message, we send it out n times in a group of n members, or n minus 1. If we have these sender keys efficiency optimization, then we send out the encryption key in O of n, and after that we can reuse it so that actual messages can be sent out in O of 1. And that is quite efficient. The problem here is that if somebody leaves the group, everybody else has to regenerate a new key for themselves because you don't want the member who left the group to be able to still decrypt messages, obviously. So we need to rotate the key, and this is actually an O of n squared, which is really bad. So to give you a comparison with a ridiculously large group, just to make it a little more dramatic, imagine you have a group of 100,000 members and you want to send out a message that is 1 kilobyte in size. So with pairwise protocols, you have 100,000 cryptographic operations like Diffie-Hellman and symmetric encryption to do that, and the payload for this one message will be 100 megabytes. So this is not going to work, of course, on an old Android phone on a 2G network. With MLS, since the whole thing is now logarithmic, we have exactly 17 operations for the same group size and a payload of only 17 kilobytes. So this might actually work on the old Android phone. And if we look at that on a chart to compare things, so client fanout is always constant in the group size in n, that's the gray bars. The sender keys, they're very efficient in the last section, in the message sending. They do that in O of 1. But for removing someone or creating a group, they're very, very inefficient because they can go all the way to n squared, actually. And so the idea for MLS was to consistently be more efficient than either client fanout or sender keys, so that adding someone is really fast. Updating keys will depend on how populated the tree is, removing as well. So we're somewhere in between O of 1 and O of n. And again, sending out a message is super fast with MLS. And we never go beyond the O of n. That is really the worst case. So end-to-end encryption encrypts the content of data. So all we talked about was the protection of the actual content and the data. So in the context of a messaging protocol, the question is also important: what do we do with metadata? How much do we have? How much do we need actually? And if so, how do we protect it? And so we should distinguish between two kinds of metadata. One is observable metadata, which is traffic patterns, for example. If you have a view of the network, you can see who is sending messages to who, at which frequency, etc., how big they are. and then there are persistent metadata. So persistent metadata is metadata that is typically on a server or at the very least on the client side. So observable metadata, that is out of scope for secure messaging protocol, because it's not something you can resolve at the protocol layer. It's something you resolve on the architectural layer with, for example, onion routing, Tor, mixnets. So this cannot be in the scope of MLS. Persistent metadata, however, that is much more interesting because we can put that in scope. And so typically servers will keep messages in queues until clients have fetched them. But we don't need the server to know who the sender is of a message long term. All the server needs to know is in which queue to put it, and then we can completely obfuscate who actually sent it. We can also have arbitrary padding so that messages all look the same size, for example, so that a server cannot really tell what kind of messages it was, whether somebody has been added to a group or removed, or whether it was an update. So we have a layered approach here where the metadata is really just in header 1, and that can be seen, and that is just the destination of a message. But everything else, we can actually encrypt that, so that only clients can decrypt it. So in the header 2, you would have the sender of the message, then the message itself, and we can, like I said, add some arbitrary padding. Deniability, which we want to do optionally. So messages need to be signed in MLS for authenticity, because we have one group key now, and if everybody encrypts under the same group key, wasn't planned, then you cannot distinguish who the sender is actually anymore. So you need a digital signature to be sure who sent the message in the first place. So for that you need identity keys, of course, and that sort of breaks deniability if you have these signatures. So what we can do instead is we can send these identity keys over a one-to-one deniable channel, so that the recipient clearly knows whose identity key it is, but cannot prove it to a third party because the channel over which they receive the key is itself deniable. And then we can, through that mechanism, we can make text messages become deniable, or even the participation in a group. And all of that can be done optionally. And of course, like I said before, the messages are encrypted under a group key additionally, so a server, which is one of the potential third parties, cannot really look at any signatures either, even ephemeral ones or deniable ones. I also mentioned federation, and I will briefly go into this on a very high level. So what needs to be done if we don't want to be tied to just one delivery service? We have this very hard requirement that handshake messages, these control messages, need to be ordered, and this is really the only problem we have to solve here. So if we can distribute this problem over more than one delivery service, we actually have some kind of federation. So imagine if you have more than one delivery service here, in this case 3, the idea is that there can be 2 levels of federations, a very simple one without any particular redundancy. So for any group conversation, you pick one of the delivery services who is going to be responsible for that particular group conversation, and who's going to be responsible for the message ordering. And in a more advanced concept, there could be some redundancy where this responsibility could be transferred to another delivery service. In the end, I want to talk a little bit about business messaging as well, because so far what I said is both applicable to consumer messengers and business messengers. And the reality is today that there is a lot more messaging going on inside of companies, simply because people are used to messaging in their private life and they want to bring that into their business life. There's an increasing number of people who don't want to rely on emails anymore because it's just an old technology. So really millennials are the problem here. For them, emails is like fax for older generations, but I think that's a good evolution. So the problem with business messaging, however, is that there are few more restrictions that apply compared to consumer messaging. Despite the fact that the users really want the same sort of experience. So one is the encryption challenge, which we've covered now extensively, and that is a problem that it doesn't scale well in large groups so far. So this is why businesses are very hesitant to introduce messengers that are end-to-end encrypted because of efficiency reasons. The other aspect is the feature challenge. So business messengers these days, they don't really federate, which is a problem. So there are silos, and then people will still use emails because everybody has an email address. You can reach almost everybody over email. So this becomes more and more of a requirement that messengers are actually able to federate across organizations, across companies. So if we want to summarize now what we said in the beginning with the wish list, I think MLS becomes really close to what we want to have here. So it's aiming to be a new standard for secure messaging, especially in large groups. It should have these modern security properties like forward security and post-compromise security. It should be robust, usable, and have an open specification. So since it's an IETF working group, all of that is available online, of course. It's being discussed on a mailing list. There is an architecture document, and most importantly, a protocol document. And the easy entry point here is this website, messaginglayersecurity.rocks, which points at the IETF website, etc., where you can find all of the documentation. And that pretty much concludes my talk for today. Thank you very much.
Thank you, Rafael. Okay, let's see if we have questions. Okay.
Hello, thank you for the presentation. My question is, because you are rotating the keys for each event, what happened with the messages that was sent in a past event? For example, if a new member comes to the group, he or she can't decrypt the past messages because it's another key.
Right.
So if you want to share information from a group, the past information, you can't. This is a problem, no?
Right, so this is not solved at the protocol layer. You're absolutely right about that. Because this is simply a consequence of having forward secrecy. So the idea here is that the protocol itself should be the most secure, and then you can build something on top of the protocol to share the history and to relax the forward secrecy a little bit, if that is what you want to do in your application in the end.
Okay, so is the duty of the upper layer to conserve the message or share it?
Yes.
This protocol acts only in the network, let's say, only to transport the message, not hide it on the application.
Exactly. So we distinguish between the protocol layer and the application layer. And the application layer will be very different for different apps. And so this is not something we would like to standardize because it's not going to make a lot of sense. And at the protocol layer, we want to be as secure and as restrictive as possible because it's always easier to relax that on the layer above. But the opposite is very difficult. If the underlying layer is not secure, you cannot just bolt on the security on top of that.
Yeah. Okay, thank you.
Thanks. Are there any other questions? No one?
What
Okay.
a silent crowd.
All right. Okay.
Yes.
Hello. In the beginning of your presentation, you presented some of messaging application that all of us are using, some WhatsApp and Telegram and so on. My question is, in your opinion, which is the most secure and which is less secure?
Well, I'm very, very biased. I work for Wire. So we try to actually be as secure as possible in the space of a collaboration messenger. But there are excellent websites. I think one is securemessaging.com, securemessagingapps.com, sorry. So somebody made the effort of going through all the so-called secure messengers and looking in detail at the properties and the promises and whether they're kept or not. So that would be a good starting point to compare.
Thank you.
One more?
Hi, thank you for the talk. So, is there a study done on where's the breaking point from normal transfer technology versus this one? Like smaller groups under 10 or under 100 people is no longer reliable to use this just because of the key changes?
So yeah, I mean the bigger the group gets, the more expensive it gets. So there is not one specific number where this is hard. But I can tell you from my experience at Wire, for example, we have been increasing the group size over time, and I think right now it's about 500 members in one group that we can still accommodate for, but it just makes things slower. So the question is, where's the pain point on the user side, essentially? And clearly we cannot do thousands or tens of thousands with pairwise protocols. That's very clear, simply because the payload is going to increase, even if the processor is fast enough.
Yeah, but the question is there a point where they're similar in speed? So to what group size should you use, conventional rather to switching?
Well, they're similar in speed for the one-to-one groups, and even as soon as you have 3 in a group already, MLS is designed to already be faster.
Okay, cool, thanks.
All right, folks, thank you so much. Any other questions, you can talk with Rafael during the breaks. Thank you so much, Rafael, for your talk.
Thank you for inviting me.